much. I'm excited to be here today to talk to you about our group's work on our CO2 capture and conversion technology, which we call reactive carbon capture. To get everyone up to speed, I want to outline two very common ways that we can upgrade waste CO2 into commodity chemicals like carbon monoxide. So in a thermal and electrochemical pathways, waste CO2 is captured in an absorber as a carbon-rich sorbent. Pure CO2 can be regenerated generally through heating of the sorbent and compressed into a usable gaseous CO2 feedstock. In the thermal CO2 reaction pathway, we use a reverse water gas shift reaction, combining CO2 with hydrogen gas at high temperatures and pressures to produce an upgraded product like carbon monoxide. CO2 electrolyzers accomplish the same chemistry, but do this electrochemically. So by applying a voltage, we can do it at mild conditions. Our group's research focuses on what we call reactive carbon capture. So the aim of our process is to skip the energy-intensive regeneration and compressing steps and not use any water electrolyzers, to use the carbon-rich sorbents directly as our feedstock. And we can achieve the exact same chemistry. So in terms of energy comparison of these three pathways, I'd like to point out that by skipping the capture and regeneration steps shown here in purple, we can actually reach parity with the thermal processes. And because we don't have any need for a compressor or regenerator, we are actually significantly less expensive in terms of capital expense to set up a reactive carbon electrolyzer. The chemistry of CO2 reduction in terms of electrochemistry is very well studied, where we're combining gaseous CO2 and water in the presence of electrons. But because our reactive carbon electrolyzer is using a bicarbonate solution as a feedstock, we need to add acid to it. So similarly to some of the presentations that you've seen earlier, we use a bipolar membrane, which we can separate water into protons and hydroxides and pump those protons into the bicarbonate solution to make the gaseous CO2 needed for the electroreduction. In all, our reactive carbon electrolyzer looks something like this. So as I said, we feed it with a bicarbonate solution, and at the bipolar membrane, it will react with protons to produce CO2 in situ, or our iCO2. This iCO2 can then be electrochemically reduced to make our upgraded product like carbon monoxide. In terms of total CO2 utilization, so this is how much CO2 reduction product you make versus how much CO2 that you're feeding your system. Our reactive carbon electrolyzer can achieve much higher utilization values because CO2 electrolyzers that are gas-fed generally use excess CO2, and the chemistry produces hydroxides, which can capture CO2 as bicarbonates, which go unutilized. Since our reactive carbon electrolyzer is generating its own CO2, we have far less excess, and any hydroxides that are produced recapture the CO2 as bicarbonate, which is just the feedstock that we're using in the first place. Our group has successfully shown that these two systems can be coupled, so we can use our CO2 capture column and a simulated flue gas to remove the CO2 from the gas stream and feed the sorbent directly into the reactive carbon electrolyzer. And we can operate this system continuously for upwards of 48 hours and constantly get upgraded carbon products. In terms of other benefits of the CO2 electrolyzers, they are generally insensitive to many impurities, such as oxygen. Now, oxygen is extremely detrimental to gaseous CO2 electrolyzers because even small concentrations will preferentially react over CO2 and will decrease the reaction selectivity or Faradaic efficiency in these plots, as you can see. But since we're using a solution-based feedstock, the only oxygen that can reach our cathode is dissolved. And that dissolved oxygen does not reach high enough concentrations to have any meaningful impact. We've also looked at other common impurities in CO2 waste streams like NOx and SOx gases, which are detrimental to gas-fed systems. In our systems, we're fortunate that dissolved SOx gases have no impact on our reaction selectivity. However, dissolved NOx gases do significantly decrease the reaction selectivity and do ammonia reduction as opposed to CO2 reduction. But I'd like to point out that in this ACS Energy Letters publication from our group, we do mention that we can use cationic surfactants to basically mitigate this effect entirely. For the reactive carbon electrolyzer to take its next steps, we need to start operating at lower voltages. So one of the approaches that our group has taken is by replacing the bipolar membrane, which is our largest voltage penalty for our system, with a cation exchange membrane. And the anodic reaction from oxygen evolution to hydrogen oxidation, we can still generate protons to generate our in situ CO2. However, we are doing a more thermodynamically favorable anodic reaction, and we don't have the voltage penalty for the BPM. But this is not the most practical solution, as hydrogen gas would need to be sourced from water electrolysis, which is an additional energy penalty. So really what our group is focusing on is looking at bipolar membranes that can more readily dissociate water, or finding cation exchange membranes that preferentially react with protons as opposed to potassium ions, so that we can still generate our in situ CO2 the same way, but we're not paying as significant a voltage penalty. And as a shameless plug for the people joining us on our lab tours, I'd like to point out that we are also using flexible automation to accelerate our materials development for the reactive carbon electrolyzer. So this is our self-driving lab, ADA. It is a team of robots that can work together without human intervention to fabricate, characterize, and test different materials in our system. Right now, we're using it to make gas diffusion electrodes. It can then take the results from these tests and use machine learning algorithms to do self-run optimization experiments. So all that we, the scientists, have to do is give it a target, come back in a week and see what it came up with, which is pretty cool to be able to work on. Finally, this is a huge team effort, and lots of people have invested in our research. So I'd like to thank everyone. And on behalf of Curtis, I'd like to thank you all for your time. And yeah, thanks.